Previously, we've seen how to do partial fraction decompositions in the case of distinct linear factors in the denominator. More recently, we've seen what to do if you have repeated linear factors in the denominator. So there is only one further complication, and that's what I want to talk about today. This is a variation on a theme of something called the fundamental theorem of algebra. Every real polynomial, every polynomial that has real numbers for coefficients can be written as a product of linear factors. This isn't quite what it looks like, though. As a simple example of this, x cubed plus 5x squared plus 6x can be factored into x multiplied by x squared plus 5x plus 6, which can then be written as x times x plus 2 times x plus 3. Each one of those three factors is linear. It may be worth mentioning that this reveals something about the graph of the original polynomial that you started with. If x is 0, then obviously this is 0, and this will be 0. If x is negative 2, then this will be 0, so that will be 0. And if x is negative 3, this will be 0 as well. The way that I could identify some information about these linear factors would be to look at the graph of x cubed plus 5x squared plus 6x and locate the places at which it's 0. In this case, that'll be x equals 0, x equal negative 2, and x equal negative 3. If I just go ahead and use my calculator to draw the graph of this, I see that when x is negative 3, or when x is negative 2, or when x is 0, the y-coordinate on my polynomial is 0. So this gives me a way of graphically thinking about how to factor things up. I can write x squared minus 4 as x plus 2 times x minus 2. So I can write x squared minus 4 as the product of linear factors. Usually when we say that a polynomial can be factored, we mean it can be split up into simpler polynomials, polynomials of lower degree, and usually when we say the word factor, we want the numbers involved to be relatively nice numbers, like whole numbers or maybe fractions, but nothing more bizarre than that. In a certain sense, though, we can factor things like this, even if the numbers are ugly. X squared minus 5 is x plus radical 5 times x minus radical 5. If you draw the graph of y equal x squared minus 5, you'll find out that y is 0 when x is negative radical 5 because of this factor, and when x is equal radical 5 because of this factor. Even though square root of 5 is not even a rational number, it's perfectly legal to reduce such a thing. So typically, if the numbers are nice, we say factor. If the numbers don't have to be so nice, we use the word reducible instead. On the other hand, if I have something like x squared plus 5, if you look at what the graph of y equal x squared plus 5 looks like, it never touches the x-axis. I cannot split this up into linear factors as I did with x squared minus radical 5. Blah, blah, blah. On the other hand, if you look at x squared plus 5, If you draw the graph of y equals x squared plus 5, it never touches the x-axis. I cannot reduce this in the sense that we reduced x squared minus 5. This doesn't contradict what we said at the beginning, though, because if you're willing to allow complex numbers into the picture, then everything is all right. X squared plus 5 is x plus radical 5 multiplied by I times x minus radical 5 multiplied by I, where I is the principal square root of -1. In most of our work, we don't work with complex numbers, though, so if I insist on only working with real numbers, there's nothing I can do with x squared plus 5. I cannot reduce it into the product of real linear factors. In such a case, I'll say that the polynomial we're dealing with is irreducible. On the other hand, the roots of x squared plus 5 are x equals negative radical 5i and x equal radical 5i. Those numbers are complex conjugates of each other. We can replace our earlier statement with this statement. If you give me a polynomial that has real coefficients in it, I can always write that polynomial as a product of things, each one of which is either a real linear polynomial or a real quadratic but irreducible quadratic factor. If I insist on sticking to the real numbers, this is the best deal that I can get. As an example of this kind of thing, I want to look at the integral of 2x over x minus 1 multiplied by x squared plus 2x plus 2. On the bottom of the fraction, obviously, I do have a distinct linear factor in the x minus 1, but I have to investigate what goes on with x squared plus 2x plus 2. If I can write that as two distinct linear factors, then we're back in the previous case. To see if x squared plus 2x plus 2 has any real linear factors, I'll draw the graph of it. I'm looking for places where that graph crosses the x-axis. Unfortunately, there aren't any. X squared plus 2x plus 2 has no places on the x-axis where the y-coordinate is 0. It has no real roots. This is an irreducible quadratic factor. It can't be written as the product of two real linear factors, because if it could, those zeros would show up on the graph here. When we were dealing with distinct linear factors, we decided that for each such thing, there would be a term in the partial fraction expansion that looks like a constant divided by the distinct linear factor. So I can write that one down. After messing with the algebra, it develops that if I have an irreducible quadratic factor that is only there one time, then the thing that I have to do is to have an additional term. The irreducible quadratic goes on the bottom, and upstairs, a linear polynomial, a first degree polynomial of form some constant b times x plus some other constant c. The problems that we've had before are now going to get worse. I have only one special number involved in this decomposition. That would be x equals 1, but I have three constants to figure out. If I clear the fraction in the usual way, I end up with this as my basic or auxiliary equation. I have a choice to make. I can take advantage of my one special number, x equal 1, and try to figure out something from that. Or I could do as we did in one of the preceding examples, just multiply everything out, simplify, and compare coefficients. In this particular one, I'm going to evaluate what happens to this situation when x is equal to 1. If x is 1, 2x is 2 times 1, which is 2. If x is equal to 1, x squared plus 2x plus 2 is 1 squared plus 2 times 1 plus 2, which is 5 times a. The second term is b times 1 plus c, which I have no idea about, but luckily it gets multiplied by 1 minus 1, which is 0. So when x is 1, the second term is not there. This tells me that 2 must equal 5 times a. That says that a is 2/5. Putting in the value for a, I can make my equation a little bit nicer. The only thing I don't know now is the number b and the number c. The 2/5 has the potential to make everything kind of messy looking. Just for convenience, I'm going to multiply both sides of the equation by 5 to make the 2/5 fraction go away. If I multiply everything out then and combine like terms, I find out that 10x needs to equal 5b plus 2x squared plus 5c minus 5b plus 4x plus 4 minus 5 times c. It should be obvious what we're going to do now. We're going to compare coefficients between the left-hand side and the right-hand side. This is actually pretty nice. The first equation, the coefficient of the x squared comparison, tells me that 5b plus 2 must be 0. That only has a single variable, namely b, in it. That's going to tell me what the b is. Likewise, that's going to tell me what the c is. So I'll have 2 of my 3 equations satisfied. The only possible point of trouble is whatever the b number that comes out of this formula and the c number that comes out of this one, those numbers have to obey this middle equation, or I will have determined that what I'm trying to do is undoable. The first equation tells me that b has to be negative 2/5. The second equation tells me that c has to be 4/5, but from that, it's not clear at all whether the equation 5c minus 5b plus 4 equals 10 is true or false. If it's false, our attempt has failed. But if I take the values for b and c and put them into this questionable equation, it turns out that the left-hand side does, in fact, simplify down to 10. So all 3 of these equations are true, and we have figured out a decomposition. I can algebraically rearrange these things if I want. In the numerator of both fractions, there's a factor of 1/5, so I can eventually pull the 1/5 out in front of the entire expression. I may as well leave the 2 in the numerator of 2 over x minus 1. In the other fraction, I am adding upstairs negative 2 plus 4x. That's the same as subtracting 2x minus 4. So I'll go ahead and write it in that format. As an aside, I have the noise reduction set on my microphone. It will be interesting for me to listen. I was going to say it will be interesting for me to listen and see if the moronic thumping noise that was coming from outside was audible. But just as I get ready to say that, the moronic thumping noise stopped. Seriously. We're into the third decade of the 21st century, and people still think thump, thump, thump is cool or impressive or whatever. Anyway, I'm going to edit that out at any rate. So, having taken advantage of this, the integral of 2x over x minus 1 times x squared plus 2x plus 2 with respect to x is the same as integrating a constant times 2 divided by x minus 1, which is easy to integrate, minus 2x minus 4 over x squared plus 2x plus 2, which hopefully will not be too difficult to integrate. If we can figure out what this last integral is, we'll be done. This doesn't look too bad, though. If you look at the denominator, it's quadratic, it's irreducible quadratic. The numerator is linear, so that's very promising looking. If you look at the derivative of the bottom, it's x squared plus 2x plus 2. The derivative of that is 2x plus 2. The numerator is very nearly equal to 2x plus 2, except instead of adding 2, I'm subtracting 4 away. It would probably be advantageous to express the top of that fraction in terms of 2x plus 2 and then make any appropriate corrections. This isn't very hard to do, though, because 2x minus 4 is the same thing as 2x plus 2 and then subtract 6 away. The reason that I'm wanting to do this, of course, is the derivative of x squared plus 2x plus 2 is 2x plus 2. This integral will be easy to do with the u substitution. You would let u equals x squared plus 2x plus 2. Du would be 2x plus 2 multiplied by dx. We are integrating 1 over u du. This integral is the natural log of the absolute value of whatever the u is, which is x squared plus 2x plus 2. And to finish the problem, we just have to figure out what to do about that. And to finish finding an antiderivative of my original function, everything has now boiled down to being able to find an antiderivative of 6 over x squared plus 2x plus 2. The 6 doesn't trouble me at all, it's just a constant factor. If I can figure out what to do with the x squared plus 2x plus 2, we'll be done. We will have one antiderivative, and then we'll append the constant of integration and have all of them. X squared plus 2x plus 2 is x squared plus 2x plus 1 added to 1. I want to express it in that way because x squared plus 2x plus 1 is a perfect square. If I think of a as being 1 and u as being x plus 1, the quantity that I'm integrating is 1 over a squared plus u squared. This is one of the things that we know how to do. Since the u would be x plus 1, du and dx would be the same thing. This integral would be the integral of 1 over 1 plus u squared du. That's just the arctangent of u, and u is an abbreviation for x plus 1. So this integral is the arctan of x plus 1. I'll take this integral, arctan of x plus 1, multiply it by the 6, put it inside the brackets, and I'll have my answer. So we now know what to do in the case of distinct linear factors on the bottom, repeated linear factors on the bottom, or even if I have single irreducible quadratic factors on the bottom. The only conceptual additional complication might be if I had an irreducible quadratic factor in the bottom that appeared more than once as a factor. I won't be asking you to do anything this complicated because the amount of algebra needed would become grotesquely large, but in principle at least, we could integrate things of the type a lower degree polynomial upstairs, I'm just writing a 1, divided by a distinct linear factor, 3 copies of another linear factor, an irreducible quadratic factor, and 3 terms are going to correspond to the irreducible quadratic factor x squared plus 2x plus 5. If I had only the distinct linear factor x minus 1, this would be the end of the story. If I had only a factor of x minus 1 and a factor of x minus 2, the first 2 terms would be the full story. Taking into account that I have 3 factors of x minus 2, though, I have additional terms, both of which have constants in the denominator, both of which have constants in the numerator, and x minus x. But because of the repeated factor x minus 2, I'll have c over x minus 2 squared and d over x minus 2 cubed as well. In contrast to linear factors, an irreducible quadratic factor will have that factor in the denominator and a linear function upstairs. So I'll have an additional term ex plus f over x squared plus 2x plus 2. That's all there is for that one because that irreducible quadratic factor only shows up once. If the factor x squared plus 2x plus 5 only showed up one time, I would have a term with it on the bottom and a linear function in the numerator. But of course, it shows up 3 times in the denominator, so we'll do something analogous to what we did for the linear factors. In principle, I could take this expression inside the square brackets here and say, I insist that that equal the quantity that I'm integrating. Then I would write the equation down that expressed that, multiply through by the denominator, and then we would go off and try to figure out the following constants: A, B, C, D, E, F, G, H, I, J, K, and L. This obviously would be a monstrous mess, but at least in principle it could be done. Once you knew those constants, though, each one of these individual terms will be relatively easy to integrate using the techniques that we've talked about previously. So, in principle at least, any rational function we can now integrate. There's one minor issue that we haven't talked about. I believe that I'll put that in a separate, very short video. So I'm going to stop with this. Coming up next is the topic of improper integrals. I hope that everybody is having a good day, and I'll talk to you again soon.